Good afternoon and welcome to Vector Institute's Research and Careers in AI. Today's session shines a spotlight on some of the wayfinders in artificial intelligence, with companies that have driven significant advances in AI and have captured our imaginations along the way. My name is Melissa Judd, and on behalf of everyone at Vector, thank you for spending this time with us, and a special thank you to our presenters, Google, NVIDIA, Thomson Reuters, and Uber ATG for sharing some of their work. I would also like to acknowledge and thank our funders, the Province of Ontario, the Government of Canada through the Pan-Canadian AI Strategy administered by CFAR, and industry sponsors from across the Canadian economy, including the 4 companies presenting here today. I also wanted to pause to acknowledge the land on which Vector is located here in Toronto, what is now a meeting place for many First Nations, Métis, and Inuit peoples, as well as newcomers to Canada from around the globe. The land we are situated on is the traditional territory of many nations, the Mississaugas of the New Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples. We acknowledge that Toronto is covered by Treaty 13, signed by the Mississaugas of the New Credit, and the Williams Treaty signed with multiple Mississaugas and Chippewa bands. We are grateful for being hosted on this land. Now, before I introduce our first speaker, I did want to remind everyone that today's session is being recorded, and there is an opportunity to ask questions of our speakers at the conclusion of our 4 talks. In the meantime, though, feel free to queue up your questions in the Q&A function at the bottom of the screen with your question. And of course, if it's directed at a specific panelist, please remember to include their name. And now for the main event. It is my distinct pleasure to introduce our first speaker, Raquel Urtasun, who will unpack the future of self-driving vehicles. Raquel is Uber ATG Chief Scientist and Head of Uber ATG Toronto. She is full professor in the Department of Computer Science at the University of Toronto, a Canada Research Chair in Machine Learning and Computer Vision, and a co-founder of the Vector Institute. Prior to coming to Toronto, Raquel was an assistant professor at the Toyota Technological Institute at Chicago. She received her PhD from the Computer Science Department at l'École Polytechnique Fédérale de Lausanne and did her postdoc at MIT and UC Berkeley. Please join me in welcoming Raquel.
Thanks, Melissa, for the kind introduction. And I'm very excited today to be here talking about my favorite topic, which is self-driving. So in this talk today, I'm going to talk about how Uber ATG is pioneering in building the next generation self-driving technology that will allow us to deploy safely at scale. In order to do so, there is 4 different things that are required in order to accomplish self-driving at scale. The ability to build vehicles at scale, the ability to operate fleets of cars, building the brain of the self-driving car such that it generalizes to many places in the world where Uber already operates today, and the network platform. The car ownership model, as you see it today, will drastically change with self-driving. Instead, you will get your self-driving car as a service, which you will call with the push of a button on your app. This will be a seamless experience where you can combine several ways of transportation. For example, you can take a bike, then a self-driving car, and then maybe your train. At Uber ATG, we don't build cars, but we have partnered with some of the best and largest vehicle manufacturers, such as Toyota and Volvo, to do so. We developed the brain in-house, and we definitely know how to build a network. We are planning to welcome both internally and externally developed technology. So you will see many different self-driving cars on the Uber network. Having the Uber network is fantastic. It means that we don't need to solve all the difficult cases from the start, such as winter in Canada, before safely deploying this technology. Instead, We will have a hybrid network where some rides will be served by self-driving cars and some by human-driven ones. Now, let me tell you how we can use AI to create the brain of the self-driving car. A very popular approach in academia is to train a neural network for the task of driving. The input to such a system is a set of sensor measurements, for example, the LiDAR, camera images, and the output is the information necessary for the self-driving car to drive. For example, steering command and acceleration. The advantage of such an approach is that it is easy to get a prototype with just a few lines of code. Furthermore, the system is trained for the end task, which is the task of driving. So every time that you make an improvement, basically your system will be driving better. However, this paradigm has several key disadvantages. It is difficult to incorporate prior knowledge and thus make the system respect the rules of traffic. It also has no interpretability, which poses a problem for the system validation and safety. And these are actually real problems when you think about deploying this in the real world. An alternative is the traditional software stack, which is composed of a set of modules executing one after another. This is what almost every competitor uses these days. Every fraction of a second, the vehicle senses the environment. This is illustrated here with a bird's eye view of the LiDAR point cloud. The first task is then to localize the vehicle with precision of a few centimeters. This is done not only to route the vehicle to the desired destination, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception task or perception system is then responsible for estimating where the objects are in the scene. Here, they are depicted with rectangles for vehicles and circles for pedestrians. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. The motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. The control system then ensures that the trajectory we intended to follow is the one that is executed, as there might be deviations due to unaccounted factors such as friction and simplistic vehicle dynamics. This whole process is then repeated every fraction of a second, typically 100 milliseconds. The advantage of this popular paradigm lies in the fact that we have interpretable intermediate representations, and it is easy to incorporate prior knowledge. However, reaction time is typically large as computation adds up. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire system, and engineers need to manually adjust their algorithms to account for those changes that other people did before. Furthermore, the different models are not trained for the end task, and thus improvements in model performance do not translate to better driving. For example, you can get a better detector, but that doesn't mean that you're going to drive more safely. Our vision, which is different from any other competitor, has the advantages of both modern AI and traditional engineering approaches, but without inherently the respective drawbacks. In particular, we believe in having a single AI system that can automatically adjust itself to any changes, thus increasing significantly developer productivity. As computation is going to be now shared across modules, the resulting reaction time is also much smaller. Furthermore, we produce interpretable intermediate representations and allow for the incorporation of prior knowledge, for example, to guarantee that we follow the rules of traffic, which is something that, by law, the self-driving car has to do. Unlike existing approaches, our AI system does complex reasoning, resulting in much better motion plans. Finally, since our approach is trained for the end task, every improvement results in better driving. Our first attempts towards this vision focus on developing approaches that can do joint perception and prediction, also called motion forecasting sometimes. That is basically 2/3 of the full software stack with a single algorithm. By now, we have developed many generations of this type of technology. So let me show you one of our latest generations that is actually running on the production system. So one of the most difficult parts of self-driving is to be able to predict the behavior of humans. This is the case as many possibilities exist, right? You can be turning, you can be continuing straight at an intersection. As a pedestrian, you can decide to cross versus not. And what is important here and makes it even more difficult is that humans not always follow the rules. To address this, our models predict multimodal probability distributions over the future locations of each actor. In the video, we display the output of our joint perception and prediction system on difficult scenarios. These are crowded scenes. You see hundreds of objects here, as well as at night, where the cameras see much less. Green boxes represent the estimated location of vehicles, and yellow circles represent pedestrians. You can see our multimodal predictions of where the actors might go in the next few seconds. Note that the system is able to reason about many actors in only a few milliseconds. And as I said, this is what is running on the vehicle. Model perception and motion forecasting algorithms still have difficulty with heavily occluded or faraway actors due to sparse sensor observations. Failing to detect and predict the intention of these hard-to-see actors might have catastrophic consequences in safety-critical situations. Another really cool piece of technology we have developed is V2VNet, the first sophisticated AI-based vehicle-to-vehicle communication approach for self-driving. It is designed to achieve the best compromise of perception and prediction performance while also satisfying existing hardware transmission bandwidth requirements. In particular, we send compressed intermediate representations of each vehicle's autonomy neural network. Then a spatially aware graph neural network aggregates this information received by nearby self-driving vehicles. Our experiment shows that by using vehicle-to-vehicle communication, you can improve performance in perception system and decrease errors by 70%, which is extremely exciting. So let's go back to our novel approach to autonomy. We have built several generations of interpretable neural motion planners as well, basically tackling the full software stack with a single algorithm. In this video, I'm going to show you our first generation, where a single model detects objects in the scene, predicts their future motion, as well as the cost volume of a sample-based motion planner. As you can see, the cost volume, which is shown here with all these colorful colors, is basically multimodal and understands rules of traffic and is able to understand things such as traffic light and produces smooth and safe driving. And as you see here, can handle very complex scenarios, for example, nudging to the opposite lane in order to go around vehicles that are parked or don't intend to actually move. Key to self-driving is the availability of high-definition maps. These are, however, very expensive to generate and maintain. It was estimated by a third party that mapping the US only once will actually cost $1 billion with P. This is one of the barriers to have self-driving at scale, as you can imagine with those costs. So we have built a state-of-the-art technology that can map online all the lanes as we drive. This technology allows us to drive hundreds of kilometers on highways without intervention and without requiring a map a priori at all, saving millions of dollars. We see this as a fail-safe system in the rare event that the map is not up to date or localization potentially might fail. But the world is even more complex. In Toronto, we say that there are two seasons, winter and construction. We have built sophisticated graph neural networks with memory that can map online complex construction sites and allow the car to react to them accordingly, as you can see in the video over here. Simulation is also very important for both test the safety of self-driving as well as to create additional training data at little cost. Recall the self-driving stack is composed of perception, prediction, and motion planning. Existing approaches in industry mostly test motion planning by giving scenarios that are composed of ground truth bounding boxes and trajectories. This is problematic as this does not really test the full system, and the results overestimate the performance of the autonomy system, as the simulations do not really model the noise coming and the uncertainty coming from perception and prediction. In order to properly test the autonomy system, we need to have a closed-loop simulator that can also simulate how the sensors, for example, the lidar and the cameras, will see the scene. Existing approaches to sensor simulation utilize virtual worlds created by artists. However, this approach is very costly and does not scale. Furthermore, there is a large fidelity gap between the real world and the simulations, thus we cannot test with confidence. Our approach is different. Instead of using artists to generate the virtual worlds, we reconstruct it automatically from data captured by our self-driving cars. This approach scales much better, and we can reconstruct every location we have driven. Furthermore, it has a much higher degree of fidelity, allowing us to properly test our systems. This picture here shows an example of a particular intersection in Pittsburgh that we have reconstructed. As you can see, these reconstructions are very accurate. Similarly, we can reconstruct tens of thousands of unique dynamic objects. Since our assets come from the real world, we have a high degree of diversity. This is not feasible with artists. In this video, you can see results of our perception system when tested in simulation on the left and in the real world on the right. As you can see in the video, the green boxes produced by perception are nearly identical when tested in our simulation or in the real world, showing a near zero domain gap. We can generate safety critical scenarios by reconstructing the world we have seen and composing it to generate new scenes. In this case, we generate a safety critical scenario that had never happened by inserting a vehicle that is coming out of occlusion in front of the self-driving car. As you can see, our autonomy software can nicely handle this case and slow down appropriately. Importantly, we can do this at scale. You can see here different variations of the same types of scenes, but with just slightly different parameters in different locations across the world. The same philosophy can be applied to video simulation, where we can enhance existing logs captured by our vehicle by inserting and removing objects. Importantly, these objects are consistent over time, as you can see in the video, and are three-dimensional, allowing us to simulate multiple cameras in the same vehicle, as well as multiple sensors in a consistent manner in order to really test our full autonomy system. Now, what separates Uber ATG from other companies is the investment on AI research, as the solution to self-driving at the scale does not exist. And AI breakthroughs are necessary, and this investment is actually happening in Toronto, which is very exciting. Furthermore, we have made all this technology available to the public by publishing all our latest, greatest AI algorithms, such that together we can solve self-driving and change the way that we live. Check out our 30+ papers this year and join the self-driving revolution. Thank you.
Thank you, Raquel. That was an absolutely incredible presentation. Thank you.